Okay, we're going to look at a couple of examples just to summarize the graphing that you have looked at in terms of quadratic functions and root functions. And we're going to look at all the different transformations and how to graph them and state the domain and range of the functions as well. So for the examples that I have, it says graph each function and then state the domain and range. The first example is f of x equals negative a half times 1/2 times x plus 1 all to the exponent 2 plus 6. So you can see that this is a quadratic function, and hopefully you recognize that by the fact that there's an exponent of 2 on the function. So what I'm going to do in order to graph this is start with my set of key points, and then based on the key points we'll think about the transformations to create the new mapping formulas, and then the points that you need in order to graph the transformed function. So I'll start by drawing my key points. And so I know the base function is y equals x squared. And so if I look at my key points, because this is a quadratic function, I want to see the U shape in the curve. And so my x coordinates that I would use are -1, -2, -1, 0, 1, and 2. And the corresponding y coordinates, if I substitute it into the base quadratic function, are 4, 1, 0, 1, and 4. Okay? Based on those key points, I'm going to apply some transformations, and I'm going to create a new set of points using the mapping formulas that I would need. So I'm going to make this table a little bit larger. Okay, so let's think about what's happening to the graph horizontally, and then we'll think about what's happening to the graph vertically. So horizontally, I'm looking inside the brackets before the function gets squared, and I can see that I'm multiplying by a half, which actually means that I'm horizontally stretching the graph by a factor of 2. And so because I'm horizontally stretching the graph by a factor of 2, that means that I'm actually multiplying all the x values by 2. Okay? And then what's happening is that the graph is being shifted to the left one. Because it's being shifted to the left one, I know I'm decreasing it by 1. Okay? So just to recap, the graph is being horizontally stretched by a factor of 2 and then shifted to the left 1 unit. Remember, all transformations that are horizontal are always the reciprocal, or they're always doing something backwards. So although this looks like it should be a compression, it's actually a stretch. And although this looks like it should be moving to the right, it's actually moving to the left. Okay? So I'm multiplying the x values by 2 and then I'm decreasing them by 1. Okay, in terms of the y values, anything that's outside of the brackets tells me that it's a vertical transformation. And so I see a few things here. There's a vertical reflection, a vertical compression by a factor of a half, and then a vertical shift up 6 units. So what that means is I'm going to multiply the y values by -1/2, and then I'm going to increase them by 6. Okay, now that we have our mapping formulas, I can apply each of these formulas to my x and y coordinates. And so if I apply it to my x coordinates, I have 2 times -2, which is -4, minus 1, which is -5. And I'll continue to evaluate in my head and calculate this. Okay, and then similarly, we're going to do the same thing with the y values. So -1/2 times 4 is -2, plus 6 is 4. -1/2 times 1 is -1/2, plus 6 is 5.5. And here I'm writing it as a decimal because I will be plotting this as a point. -1/2 times 0 is 0, plus 6 is 6. And then I can continue to do this as well. Okay, and one way to confirm that your key points are most likely correct is to look at your original vertex and see whether or not it's moved to where you're expecting the vertex to be. So if I look back at the function, I know that the vertex should be left 1 and up 6. So, and that's exactly what I have, left 1 and up 6. So I can plot these points. And I'm going to continue to plot the points. And what you'll notice is a very short but very wide graph. Okay? The graph is fairly short because the graph has been vertically compressed by a factor of a half. And you'll notice that the graph is very wide because the graph has been horizontally stretched by a factor of 2. So those are some quick ways for you to verify that what you've graphed is correct. Okay? I'm expecting a short but wide graph as a result of the transformations that I had. Okay? The graph is also opening down because of the negative at the front. So I have a feeling that I'm on the right track, and most likely we've graphed the function appropriately. Okay, so I'm just drawing my arrows and my function. Don't forget to label your graph. So this is the graph of f of x. Okay, so there's a label as well. Okay, the last part is to state the domain and range. So x is going to be an element of all real numbers such that, and in this case actually there is no restriction on how far to the left and right the graph can go. So the domain of the quadratic function is all real numbers. And in terms of the range, we have y is an element of all real numbers such that, and you'll notice that there is a restriction on how high y can go, and the highest value I have for y is 6. All the other values are less than that, so I know that y is going to be less than or equal to 6. Okay, let's take a look at our second example. In this example we have a root function. And for this root function, again, we're going to graph it and then state the domain and range. This one's a little bit different though. And the reason for that is because you'll notice that the horizontal transformation is not in factored form. So our first step is actually to factor this. And so I'm going to write this in factored form. And by factored form, I mean if there's a coefficient in front of the x, you need to have it factored out. So you want the coefficient of x to just be 1 inside the brackets, much like what we had up here. Okay? So the first thing I'm going to do is factor out the negative 2. And so what I'd be left with is x minus 4 inside the brackets. And the reason why this is so important is because if you don't have it in factored form, then although your stretch or your compression is going to be fine, your shift left or right is not actually going to be the same. So you want to make sure that it's in the factored form so that you can see what each of the transformations are. Okay, so again, I'm going to start with my key points. And this time I have a different function. And you can identify what kind of function is by the symbol that's used in it. And I can see a root function in this case. So I see the square root sign. So I'm going to use the key points for a root function to start. And so the key points I would use in order to have some nice values to work with are x values that are perfect squares that I can actually find the square root of. So 0 is the smallest number I can find the square root of. 1, 4, and 9 are the next few numbers that I can use. And so the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is equal to 3. And now I'm going to determine what my mapping formulas are so I can create my new points. And if I look at the horizontal transformations, again, your horizontal transformations occur before you apply the function to the actual numbers. So, or to the actual x value. So if you look at what's happening here, where the x value is, that's where all your horizontal transformations are, underneath the square root. So I see a horizontal reflection in the y-axis, a horizontal compression. Remember, it's always the opposite of what you think it's going to be. Horizontal compression by a factor of 1/2. And then a horizontal shift to the right 4 units. So what that tells me is, because the graph is being reflected, I know I'm multiplying the x values by negative. And because this is actually a compression by a factor of 1/2, I'm going to multiply the x values by 1/2. And then I'm going to shift the entire graph to the right 4. So I'm going to add 4. Okay, for the y values, it's anything that's outside of the square root sign. So I have 2 numbers that are outside of the square root sign. And so that tells me I have a vertical stretch by a factor of 3. So I'm going to multiply the y values by 3. and then I have a vertical shift down 3, so I'm going to subtract 3. Okay, so if I apply these formulas to my x and my y coordinates, negative a half of 0 is 0 plus 4 is 4. Negative a half of 1 is negative a half plus 4 is 3.5. Negative a half of 4 is negative 2 plus 4 is 2. And negative a half of 9 is negative 4.5 plus 4 is negative 0.5. Same idea for the y coordinates. So 3 times 1 is 3 minus 3 is 0. And there's your y coordinates. Okay? And again, what you want to check is that the initial point has moved to where you expected it to move. So the initial point used to be at 0, 0, and now it's moved to 4 and negative 3. If you look at the transformed graph, the root function has been shifted to the right 4 and down 3. Right 4 and down 3. That's exactly what you're expecting. So now you can plot your points, and this tells me that this is where my graph is going to start, and then it's going to continue in one of the directions. So I'm going to plot my points. So 4 and negative 3. And I'll continue to plot the points. And so that's what the points look like. Now, if you look at this graph, it looks like a very narrow but tall graph. Okay? It's narrow because you've compressed the graph by a factor of a half. So horizontally, you've made it skinnier. And it looks taller, and that's because the graph has been vertically stretched by a factor of 3. So it's 3 times as tall as it normally would be. Okay? Also, remember that your initial point is at 4 and negative 3. The graph is going to move up and to the left, and it makes sense that it's moving up and to the left because the graph has been reflected. So instead of moving up and to the right, it's going to move up and to the left because it's been horizontally reflected. So it'll look like that. Okay, so this is the graph of g of x. The last thing we're going to look at is the domain and range. So x is an element of all real numbers such that, and you'll notice that the range has a restriction on it. It's got a higher most amount, and the highest amount you can have is 4. And so all the other values of x are going to be less than or equal to 4. And in terms of the range, there's also a restriction on the range. It's got a lower limit. All the values of y are going to be higher than this number, and they're all going to be higher than or equal to, so greater than or equal to negative 3.